you can start. You can start now.
All right.
Okay, let's go.
All right. So, good afternoon to the great people of the free astro science. So, welcome back again to our lecture series. My name is Miracle Marcel, and I will be lecturing on galaxies. So, in this lecture, today's lecture, I'm going to be introducing galaxies. Then other subsequent lectures, I'm going to explain more about galaxies. So from the table of content, I'm going to be exploring how we can start exploring galaxies, the meaning of a galaxy, then the history of discovery of galaxies, then the great debate and the modern discovery of galaxies. Then I'll end up with the Hubble classification of galaxies. I hope I can end this lecture within an hour because it's going to take us a couple of time. So how can we start exploring galaxies? You know, all the stars we see at night are in our Milky Way galaxy. So if you look at this picture, you can see every inch of space is occupied by stars. So how can we now see galaxies if every part of the sky is occupied by stars? Everywhere we look, we see stars everywhere. So how we can do that is maybe if we have a powerful telescope like the Hubble Space Telescope or the James Webb Space Telescope, we can decide, okay, let us look at this patch of the sky, okay, at this patch of the skies that are a little bit darker. Maybe if we point our telescope to that point, we can pierce through and see other galaxies. Maybe that is cool. So if we do that from this picture, if you put our telescopes around here and we zoom in well enough, then we can see galaxies. We can see something like this. So this is called the Hubble Ultra Deep Field. Okay, so the pictures you are seeing here, we are taking in the UV rays, the visible and the ultraviolet spectrum. Okay, so it is used to demonstrate, okay, it is used to explain that even a tiny patch of the sky, even a tiny patch of the sky can contain countless galaxies because the universe extends far beyond what we can see with our naked eyes. So in this double deep field picture, there are about 10,000 galaxies here, just a little patch of the sky, about 10,000 galaxies. So you can imagine how numerous galaxies are in our Milky Way galaxy. So in our universe. So in the subsequently, I'm going to talk about the numbers of galaxies, maybe not in this lecture, but in the future lectures. I'm going to talk about the number of galaxies and how it was possible to count them. So this is the video of what I have just described. Okay, just locate a patch of the sky, a good specimen, and you focus your telescope there, a very powerful telescope, and you keep zooming in. You're going to zoom past the stars in our Milky Way galaxy. Then you continue zooming in until you reach to the ends of the universe. So it's coming. So you keep zooming in. So if you keep zooming in, you're going to get to the Hubble Ultra Deep. So although this is like there was a kind of an editing there, but this is how it works. So you zoom in and you until you get it. So here is an example of one such kind of image. So this is a galaxy cluster. Okay, here's a galaxy cluster called SMARCS J0723.3. It was one of the first data release of the James Webb Space Telescope. So if you look, you can see galaxies, okay? And you can also see some stars. These stars they happen to be on the way of the James Webb Space Telescope, and they are stars in our Milky Way galaxies. So they are not at the same distance as these galaxies you are seeing here, okay? So So this is an example of galaxies. So if you zoom in, you're going to see these kind of things. And you can see that some of them are a little bit bent. This is called gravitational lensing. Gravitational lensing. This was taken from a very tiny patch of the sky. All of these pictures. So you see, galaxies are as abundant as the sands on Earth. So what is a galaxy? So a galaxy simply means a system, a vast system that contains stars, okay, dust and gas, then planets, dark matter, and all of which are bound together. Just like we say an atom is the smallest particle of an element, okay? Or maybe we say a cell is the, like, how we define it in biology about a cell. So in the same way, a galaxy is the building block of the universe. It is the building block, okay, so of the universe. And our Milky Way galaxy, that as the picture you can see here, happens to be one of many billions and billions of galaxies. So how did historical people perceive this galaxy? Okay, how did ancient people perceive it? So before telescope was invented, okay, the Milky Way appeared as a faint, cloudy band across the night sky. Look at it here. So in the ancient times, people saw this. They saw this, and they could not fathom what it was. So some of them were coming up with a lot of mystical explanation. Okay, so for instance, in the 15th century, the Greeks, there's a man called Democritus. He suggested that the Milky Way galaxy may be composed of distant stars. He was really smart enough to do that. Then Aristotle, in the 14th century, proposed that it is not, it is actually it is from our atmosphere. It is an atmospheric phenomenon, okay? So then the Chinese and the Arabic, they recorded star maps and described nebulae like objects. So even the Egyptians, they come up with this. In fact, the Egyptians believe that once someone dies, their soul goes to the great beyond over there. So they have a lot of mystical explanation or interpretation about the Milky Way galaxy, about this. But then Galileo came up in the 17th century with his telescope. So he used his telescope to observe planets and the sun and the Milky Way. He used his telescope to do a lot of things. So, and his work provided the evidence of a heliocentric model of heliocentric model is a model that describes the sun as the center, okay? So away from the geocentric that says that Earth is at the center. He also used it to observe other stars. So his work demonstrated that the sun is a star and the Milky Way was not a cloud, but a vast collection of stars. So his work insinuated that the sun is at the center of the universe, where the stars are somewhere in what we call the celestial sphere. So his work gave an insight into our position in the Milky Way galaxy and in the universe altogether. Then here comes Charles Messier. Charles Messier was more interested in comets. So he was more interested in detecting comets. But, you know, there's a lot of stuff in the sky, okay, that looks like it, like the nebulae. So he started to make catalogs of nebulae so that he can distinguish them from his comets. So some of these nebulae included galaxies. Okay, the galaxies as we know them as of today. So it included galaxies, star clusters, and gaseous nebulae. So to avoid confusion with comets. And then we have the William Herschel. In 1785, he drew the map of the Milky Way galaxy. To them, as of that time, it was the map of the universe because they thought it was just the whole universe. Because Kepler, Galileo came up, his idea insinuated that our sun is not all that it is, that these stars are just like the sun. So William Herschel now drew the map of the whole world. So this is the map of of the galaxy he drew, okay, based on their limited tools and knowledge as of that time. Then here comes the great debate. The great debate as of 19th and 20th century. So they were debating where the location of this nebulae. Okay, so they want to know if these nebulae they are seeing are part of the Milky Way galaxy, are part of the star system they see at night. The star system are part of the star system they see at night. So because they saw some distinct features from these nebulae. Like for instance, they saw spiral nebulae. They call it nebulae. They saw spiral. They call it spiral nebulae. Some called it white nebulae. So some of them speculated that these nebulae are part of the Milky Way galaxy. Okay, so while others suggested that these are different universes. Okay, these are different worlds. So there are different star systems beyond the Milky Way. You understand? So these were the two debates. So there was no clear winner at that time, but the debate set the stage for the breakthrough discovery. So now comes the Hubble. Edward Hubble in the 1920s. He used his powerful telescope, a 100-inch Hooke telescope, at the Mount Wilson Observatory in California to observe variable stars in Andromeda Galaxy. Okay, variable stars are kind of stars that they are they change in brightness, and the period at which the change in brightness can be computed. Okay, so there is a relationship between their period, and their luminosity. So we use them as standard candles. Even before Hubble started to make this observation, astronomers have detected variable stars even in our globular cluster. So they are able to use some set of equations to calculate distances to these variable stars. So Hubble coming into the scene, he used that same idea to calculate the distance to those variable stars in the Andromeda Galaxy. And that gave him, he compared those distances to the distance to the ones in our Milky Way galaxy, and discovered that they are so discrepant. So that is how he proved that the Andromeda Galaxy was far away outside our Milky Way galaxy. So he also did that with other galaxy types. He also did the same findings, the same observation on other galaxy types, and published his work in 1924, confirming that the universe contains many galaxies. So here is in the picture of the Andromeda Galaxy, and this marks, he was the one that made these marks to pinpoint those variable stars that he studied. So here is the Hubble making his observation. So now he gathered those galaxies because he observed so many galaxies, and he built a scheme called the Edwin classification scheme. So where he classified galaxies according to how they appear. So after classifying them, the classification, the scheme looked like what we call a tuning fork. So that's what we call it the Hubble tuning fork. This one is it's an upgraded version of this one. It was later added. Okay, so and what was added there is irregular galaxy, because initially Hubble did not add irregular galaxies. So the Hubble scheme divided galaxies into three broad classes based on their visual appearance. So we have the elliptical galaxies, we have the spiral galaxies, we have the bar spiral galaxies. These are the same. They are the same spiral galaxies, okay? But we do not regard them as different, okay? But here we have bar spiral, then we have the spiral. And I'm going to explain the difference, okay? I'm going to explain the difference. Then we have the irregular galaxies. So they are still the three broad classes. So in the elliptical galaxies have smooth, featureless light distribution and appear as ellipses in images. Okay, their shape range from nearly spherical to elongated oval. So if you look at this picture, so look at this is nearly spherical, and as you move towards to the right, they become more and more elongated, like a cigar shape or like an egg. Okay, so they are denoted with the letter E followed by an integer n. So that n range from 0 to 7. So for n equals to 0, it means for like the spherical ones, then we have 1, 2, 3 to 7. Okay, so now generally for these elliptical galaxies, okay, they are primarily dominated by old stars. Okay, they are primarily dominated by old stars, and there is little or no star formation going on, and this is because they have little or no dust, little or no gas and dust left to form new stars. So they have no spiral arms or complex structure. They are just very simple, like an egg. They have no complex structure. So some of the largest galaxies that we have seen so far are elliptical galaxies, okay? And they are found in galaxy clusters, although I have not explained the meaning of galaxy clusters, but you can imagine it as star clusters, a group of stars, together in the sky. So we have galaxy clusters. I'm going to explain that in the future. Then elliptical galaxies account for about 1/3 of all the galaxies in our Milky Way galaxy. So you can imagine E naught as spherical. So this is leading us somewhere. You can imagine E naught as being spherical in shape. Then as you approach E1, E2, E2, E7, it becomes like a rugby ball. It becomes very, very elliptical, like a cigar shape. So this is leading us somewhere. So I want you to bear that in mind. E naught galaxies, they are elliptical, we call them elliptical galaxies, but they are spherical in shape. They are nearly spherical in shape. So example of elliptical galaxies are NGC 1379. It's spherical. We have always known galaxies to be flattened, but we have spherical galaxies. We have very elliptical galaxies. Then we have E3, M86 is an example of an E3 elliptical galaxy that has n equals to 3, according to how we observe it from the sky. Then we have M59, like as an example of E5 galaxy type. And then we have very, very, very elliptical galaxy E7. Very, very cigar shape. Okay. This is not edge on, okay? This is not edge on, so that you don't confuse it like maybe we are observing it from edge on. This is a whole galaxy looking like that. Very, very shocking. Then we have the spiral galaxy. So spiral galaxies consist of flattened disk, okay? Flattened disk with stars forming a spiral structure and a central concentration of stars known as bulge, which is similar to the appearance of an elliptical galaxy. So here is a picture. There's a picture of the elliptical galaxies here. Okay, so they consist of flattened disk. Okay, now, and this disk has stars in them. Okay, they have stars in them, but then they have their bulge. Their bulge looks pretty much like ellipticals, all the ellipticals from the E0 to E7. Okay, so they are so the bulge or the nucleus are similar in shape to the elliptical galaxies. Okay, so and they are denoted by the symbol S. So in terms of star population, so they have a mix of young hot stars, okay? And these young hot stars are located in the spiral arms, while the old stars are located at the bulge or at the nucleus. So Hubble classified the spiral galaxies into two. So we have the S0, SA, SB, and SC. So this is classified with respect to the size of the nucleus or bulge. I'm going to explain that in details. Then we have the SBA, SBB, and SBC. So you can you can imagine it as spiral bars, but we call it bar spiral. Okay, it's bar spiral galaxies. I'm going to explain that in the future. But I want you to, I want to make an analogy here. I want to make an analogy here. Remember what I said about electrical galaxies? Remember what I said about electrical galaxies? This is the one of E naught, and this is the one of E7. So it moves. Now, so imagine, I want you to imagine, wait, I want you to imagine the SA, SB, and SC galaxies as some kind of E naught galaxies with clouds around them, with a flattened cloud around it. Remember, I said that E naught are they are spherical, okay? So now for the SA, SB, and SC galaxies, they are just like E naught galaxy, but with some kind of flattened disk around them. Okay, so I want you to picture that. Why for the E1 to E7, okay, they tend to become SBA, SBB, and SBC. So they are just like electrical galaxies with some things surrounding them. With some, I use a cloud here, but in the case of galaxies, they are cloud of stars forming a spiral structure. So I hope you can understand the picture I'm trying to portray here. So now, as an example of one of those spiral galaxies, so the S naught, or we call it the lenticular galaxies, they are a hybrid. They're like a combination, like a hybrid between the elliptical galaxies and the spiral galaxies, in that they have a central bulge and a disk, but lack prominent spirals due to the depletion of gas, meaning they have very, very low star formation activity. Okay, so they have very large nucleus, okay, but with hardly visible, very tightly worn spiral arms. So let's say example NGC 4866. So for the other types of the spiral galaxies, like I said about, I talked about SA. So you can imagine it as E naught, but with some spirals around it. Okay, but now the bulge is large, okay? The bulge is large, and the spiral arms are almost not even noticeable, okay? So they have a very bright central bulge and the very tightly worn spiral arms with little star formation. That makes a lot of sense because the bulge is known for having little star formation, even for ellipticals. Then we have the SB. As you progress, so they have medium-sized bulge. So now in the SB, the bulge is going to reduce. Then you can imagine it as if the bulge reduces, it goes into the spiral structure of the galaxy. So they have moderately worn arms with more star formation activity than the SA. Then we have the SC. The SC, they have very small bulge, almost no bulge, okay, and loosely worn arms with significant star formation. So you can imagine so there's a reciprocal law going on there. The more the bulge, the less the star formation activity. So here is an example of SA M65. We have the Andromeda Galaxy, okay, SB. Andromeda Galaxy of all people, our closest galaxy is an SB galaxy. Then we have the Triangulum Galaxy. So this galaxies are it almost has no nucleus. So the Triangular Galaxy is an example of an SC, it's a spiral galaxy in the C class. So little or no star formation happens at the bulge, and active star formation are active at the spiral arms. That's just the summary of these spiral galaxies. Then we have the other parts of the spiral galaxies. So now, roughly half of all spirals are also observed to have ball-like structures. So like, you can imagine them as those rugby balls, rock or egg-shaped galaxies, like we saw in E1 to E7. Okay, so most of the galaxies are like that. Almost half are like that. So extending from the central bulge. So these bar spirals are given the symbol SB in capital letter. So for the SBA, so just like we have understood for the spiral galaxies and from the elliptical galaxies, for the SBA they have large, bright central bulge and very tightly wound spiral arms with little star formation. Then for the SBB, medium-sized bulge, moderately worn arms with more star formation. Then we have SBC, loosely worn arms with significant star formation. So here's an example. An example is NGC 4262 SBA. Then we have NGC 1300 under the SBB. Then we have the NGC 1364 under SBC. Fact, it is believed that our Milky Way galaxy, our Milky Way galaxy, like we studied before, has a bar. It has a bar. So some studies are suggesting it belongs to the SBB or SBC class. So how about the irregular galaxies? How about the irregular galaxies? Like as the name implies, irregular galaxies lack clear shape, like the spirals and the ellipticals. If you're looking at those galaxies, you don't even know what to call them. Okay, so they appear asymmetric and very chaotic, often due to gravitational interactions. Maybe two galaxies are interacting with themselves. Maybe two close galaxies, the gravitational distort themselves. Okay, or maybe two merging galaxies. If two galaxies merge, their shape is going to be distorted, or internal disturbance, okay, some internal mechanisms. So these galaxies typically contain large amount of gas and dust, making them site of active star formation and home to many young hot stars. So an example of this is the large and the small Magellanic Cloud. These are the satellite galaxies orbiting our Milky Way galaxies. We are trapped by the gravitational influence of our Milky Way galaxy. So here's the summary of all the galaxies we just read it. According to the Hubble scheme, we have E0, elliptical galaxies, we have the spiral galaxies, and we have the irregular galaxies. So how about, I want to introduce you to a citizen science project called the Galaxy Zoo, where you can classify galaxies according to how I've explained them in this lecture. So Galaxy Zoo is a citizen science project that invites the public to help classify galaxies using images from powerful telescopes. The project began in 2007 and has become one of the largest astronomy-related citizen science initiative in the world. So it is hosted in the Zooniverse platform and is managed by a team of astronomers and data scientists. So I would, if you want to contribute your effort to classifying galaxies, because new galaxies are being observed every day, we classify them. Okay, so you can Google Galaxy Zoo so that I can get involved. I've been involved in this project since 2020 till now. So this is the end of my lecture. So in my next lecture, I'm going to give more facts about galaxies. Thank you so much for paying attention.